comparing means is something that we will do quite frequently inside our usability testing. We may have a couple of different prototypes. We may have collected data in terms of, for example, user satisfaction. And we want to answer questions like, well, does users prefer the second prototype over the first prototype? So in that sense, we'll take an average value, for example, an average rating, and we'll compare the mean between these two different sampled values. We need to be careful in terms of how we do this, that we can do it in a way where we can indicate and show our degree of statistical confidence around it. There's a range of different types of tests that we can use, and in this we'll use different types of t-test or an ANOVA. And one of the fundamental questions we need to ask first of all, and this will help us understand what is the appropriate type of test, because the tests will all fundamentally do the same thing, they're just designed for different types of data, or rather there's some that are more appropriate to certain types of data. So a key question that we'll always want to answer up front is in terms of the type of data that we have collected. So in terms of this here, it's going to be a question of, are we using paired samples or independent samples? A paired sample is where we're comparing different outcomes using the same group of people. So we had a group of 10 different users. We showed them all option A, we showed them all option B, and we've asked each of the users to give their ratings on it. So we'll know for our first user what that individual thought of option A and what they thought of option B. So in that sense, they are paired samples. For each user, we have the results for that particular user. If they're independent samples, this might arise, for example, where we had 10 users who were testing the first prototype and a completely different set of 10 users who were testing the second prototype. So in that sense they're independent. We know for the first set of users what they thought, we know for the second set of users what they thought. Now, that's an important element because that will determine what particular type of test that we're using. If we are comparing two results, then that's going to be two different means that we're comparing together, in the case we had two prototypes. If we had, for example, three different prototypes, we might be looking at three different average values and asking, do those three values meaningfully differ amongst themselves? So these are the important things. If we are dealing with two samples, so we've got two different options and we want to compare the means, we will be using a t-test. There's going to be different flavors, independent or paired, depending upon the data we've collected. If we have more than two, then we're going to be using an analysis of variance or an ANOVA test to do that. In all cases, we'll be making use of Excel because it offers this functionality inside it. But key thing you need to answer first of all is, for the data you have collected, is it paired samples? Are they independent samples? And are you comparing two average values or more than two average values? If we start off first of all thinking about comparing independent samples, it's not really much difference when we look at paired, but let's look at independent first of all. And here we show an example on the screen where we're looking at two independent samples, so two different groups of users evaluating two of our prototypes. We've got a mean value, an average value, and we've calculated and shown a confidence interval around that. So let's say it's 95% confidence, and we've got our confidence bars shown for the particular values. If you wanted to then ask the question, okay, so we know on average what the users felt for both of them. We know our intervals to be 95% confident for both of them. Are we content? Are we certain that there's a meaningful difference between the two? Can we say with conviction that the users preferred one over the other? Or are the things sufficiently close or overlapped that we can't conclude anything? So there's a few things we can do just to narrow down what type of test we need to use, if we need to use a test at all. The first bit, if we consider an example where the confidence intervals don't overlap. So we have it for our first one, the particular interval, and the second one to the interval for that. And if they are non-overlapping, there's a gap between them, then we don't need to do another test. We can quite confidently say at that point that the means are significantly different at whatever level of confidence we have calculated the intervals based on. So for the first case, we can be 95% certain over here that these means are significantly different. If we look at another case where we've calculated, again, our two averages, the averages are the same here, we're just varying the confidence intervals, and the intervals overlap a bit, so there's a bit of overlap. It's possible that the real population mean could be down here and also could be up there. There's a bit of an overlap. In that case, if they partially overlap, we should then test to see, are they meaningfully different? And in this particular case, because we're dealing with independent samples, we should use an independent two-sample t-test. That's the particular test that is an appropriate one for us to work out if we have overlap. And we'll look at that on the next slide. Finally, in terms of this sort of initial introduction, if whenever we look at our samples and they very significantly overlap, so there's a lot of overlap between them, at that point we don't even need to do a t-test or any other sort of analysis. If there's a lot of overlap in the confidence intervals, we can't say that these things are meaningfully different at our chosen level of confidence. So we'd have to conclude then that the means are not different at a 95% level of confidence in this particular example. So let's have a look then at our independent two-sample t-test. So we said we would use this if we're dealing with independent samples, and we'll look at the paired samples shortly. We've got two things we want to compare, and what we've looked at it, and we know there's a bit of overlap between our confidence intervals. So we want to use a t-test then to determine if we can be 95% confident that these things are significantly different. Now for a t-test, it's going to contain two things. We're going to calculate a t-value, and we're then going to compare that to a value that we will look up or use an online calculator to work out. And the t-value is the thing we want to have a little bit of explore in terms of how it is calculated, just to understand the different parts. And you can see it's here known as t, and it measures a ratio of two different aspects. The first one measures the ratio between the two sample means, and what the ratio is then is the variance across both of the samples. So let's think about this. So under the top bit over here, we're calculating the distance between the two means. Now our t-value, if it is above our value that we get from the table, we're going to conclude that they are different. That's how the way that we'll use the t-value. So in terms of this calculation here, we would take away the two means. If the means are far apart, we'll end up with a bigger value than if the means are close together. So that's going to reflect this here. The bigger the distance between the means, then the more positive or confident we can be that they meaningfully different. Whereas the closer together the two means are, then the less confident we can be. We're going to divide this then by a value that basically represents the amount of variation across the two different samples. So we're combining the two data sets and just having one measure of variance. And again, this kind of makes sense, because if we have a large amount of variance, so we take our two sets of data, we combine them together, we calculate the variance, and it's a large value, it means there's a lot of variation inside that data. That will act to make the t-value smaller, because we're dividing by that large value. If there's a small amount of variance, so there isn't too much variance when we take the things together, we will be dividing by a smaller value, so overall our t-value then remains larger. So when we're calculating our t-value, the further the way the means are, the higher the value, and the smaller the variance is, the higher the value. And that's the two different factors then that give us a measure of just how separate, how distant these are, alongside a measure of the amount of variability that we have inside it. You can see on the screen here, this is just the calculation. If we have the two different sort of variances, really sort of standard deviation we're calculating here, so the two different variances divided by the number, add them together, take the square root. It's just a way of calculating that combined variance of those two different samples. Now that gives us our t-value. As we said, we're going to compare this against a value that we'll look up, and we're not really interested in how we calculate this looked up value. It's just something we'll plug into an online calculator and get the value back. There's two variables that we input in to determine what are our comparison, known as the critical value that we're comparing it against. The first value that we're going to use to calculate our critical value is the level of confidence. So as our confidence increases, then that will give us a larger critical value. So we're going to have a higher t-value if it's going to be meaningfully different. The other one is a measure of the degrees of freedom. So degrees of freedom, it's just simply a basic measurement of how much variability went into the data set. Normally, it's the number of variables that you have, the number of users in this particular case. So the more users, the higher the degree of freedom. Because we've got two samples, we sort of normally add those things together. So we have a value where degrees of freedom, but it's calculated based on the number of the sample size for both of our samples. We'll plug that in, we'll get a critical value output from that, and we'll then compare that against our t-value. And if our t-value is smaller, it's less than the critical value, in that case then we can't conclude the means are different. If our t-value is greater than the significant value, then we can conclude. We can say we're 95% certain that these means are significantly different. So I have a small example here in this slide just to show it. And we'll start off first of all just looking at how we can do it inside Excel, and then we'll look at an actual example. So thankfully Excel offers this functionality built into it. It has a t.test function where you pass in the two arrays that contains our data, and then it takes in two other parameters. The first one tells us about the tails, and the second one tells us about the type. For the tails, is either 1 or 2 depending on whether it's a one-sided or two-sided distribution. For the types of things that we're dealing with, we'll always select as a two-sided distribution. So 2 is the default value we'll put in this. The type then is going to be the type of t-test that we want to perform. If it's 1, it's going to be a paired sample. We'll look at that in the next slide, but here, remember, we started off, we're assuming we're dealing with independent data. So we're not going to use paired, we're dealing with independent. So option 2 and 3 are the ones that we would use. And we'd use option 2 if we think the variance, or if we know the variance is roughly the same between the two samples, or if we feel actually the variance is quite significantly different, we would use option 3. So that's simply it. So we can plug those in. Excel will then give us back a value. Now, the value that Excel gives us back, we need to be careful about the interpretation of this. So it's going to give us back a value, and we'll see the value is 10.1%. That is the chance, the probability that the true means are going to be the same, that we can't tell them apart. Now, let's look at the example, then we'll come back to this particular one. So example over here, we have two different user ratings. Remember, they're independent. So we've asked one group of users to rate something out of 5, and they've given us values 4, 2, 1, and so on. We've asked a second group of users to rate another thing out of 5. It's a slightly bigger group, that's okay. We can plug those values in, doesn't make any difference to the t-test for independent values. So 11 users did the first one, 13 did the second. Our standard deviation, 1.43, 1.05. Let's say they're sufficiently close that we think, okay, we'll just use type 2 for our more or less equal variance. We're going to use a 95% confidence interval, and if we were then calculating those particular values and plugging it in, we'd get 0.85 and 0.57 as our critical values then that we have for that. Or sorry, the confidence interval is 95%, plus or minus 0.85 and plus or minus 0.57 in terms of our confidence intervals that we have for that data. So plugging all of that into a t-test, we'll see here we've got our two average values. We can see we've got our intervals. We can see there's a little bit of overlap between them there at the bottom, so it's appropriate to use a t-test. We put all of those things into our t-test. and we would get out a value of 10.05%. So that is telling us the probability that these two tests are not significantly different. If we were dealing with a 95% confidence, that's our level of confidence that we're working at, we could only conclude here that we cannot be sufficiently confident. We cannot be 95% confident. We can't really be 90% confident. So in this sense, we'd have to conclude at a 95% level of confidence, we cannot say that these means are different. So it's really, really useful as a way then of being able to understand and compare our means. It also highlights, I suppose you could show this particular graph to somebody and you could say, well, look, the means definitely differ and the confidence intervals only slightly overlap. But if you wanted to be 95% sure in it, you're not permitted to make that conclusion. Paired samples is the next one we'll have a look at, and this is very, very straightforward because it's all going to be exactly the same analysis we had before, except we're dealing with paired samples. We're going to use the same sort of t-test, but we'll change it then to option 1 in terms of the type. Now, the interesting thing about paired samples, and we should use that there when we know that we've been using the same group of people to generate the results. And as I said, we simply put in option 1. Paired tests compare each person to themselves. It's saying that, okay, in the first test you did this, and in the second test you did that. As opposed to, if they're independent, it was one person did one and some other person did the other one. Because you're comparing the person to themselves, differences are more significant. You can assume that people are more or less the same, and where you then are observing differences, they do become more significant. So for paired samples, is easier then to be, when you see differences, is easier then to become more confident that they are meaningful. I have an example here. I might as well just talk through this here. So let's assume we had paired samples. So it's the same group of users. So in this case, we have a total of 6 users. And those 6 users did the first one, and they also did the second one. So they have to be paired, they have to have the same number. In terms of our standard deviations, we've calculated them as such. In terms of our 95% confidence intervals, it's plus or minus 0.79 and plus or minus 0.6. So if we were showing this then on a particular graph, we would end up with this case. You can see the two means, you can see the two confidence intervals, and again, they overlap. We go into Excel, we take our t-test, we plug in the 2 arrays, two tails, and we say type 1 for paired. And we do all of those, we get a t value, or the output from that will be 3.35%. And that, from Excel's point of view, is the probability then that they're basically the same mean, or they're not significantly different. If we were operating at a 95% level of confidence, then that's less than 5% in terms of our error rate. We could say at that point, or we would say at that point, we are 95% certain or confident that these means do significantly differ. And the reason we can say that there is that it's because we're using paired samples. If that was unpaired data and we plugged in exactly the same thing, so we assume then these are just independent samples, we change our type to, let's say, 2, we would have our probability that we can't tell them apart would increase to 8.3. So you can see the impact then, or the effect that using paired samples has in terms of our ability to be more confident about our data. Let's assume we have a case where we want to compare more than 2 samples. So this might be the case where we have a number of different prototypes. We've got our users to do all of these prototypes, and we've got average values, and we want to work out, well, do they meaningfully differ? T-test, we can't really use, we can do 2 for a t-test, but if we have more than 2, we can use an analysis of variance and ANOVA test for doing that. There's different types of ANOVA that are defined and available through Excel. We want to use a one-way or a single factor, because if we're just comparing one mean, that's the particular one that we would use. The thing to note about the ANOVA test is it's going to tell you if the means are significantly different. It'll be a yes or a no. If it says no, they're not, that's fair enough, it's job done. If it says yes, they are significantly different, it won't identify which means are significantly different or not, which pairings. So if ANOVA comes back and says, no, there's some meaningful difference between these means, then you quite often need to go down to using a t-test just to understand which individual pairings are significantly different between themselves. These are available inside Excel, but one of the things about using ANOVA tests is that it may not necessarily be available out of the box in Excel. Excel has a number of plugins. You can Google this for adding the thing in, but you need to add in the analysis tool pack. And as part of that, you'll get access then to the ANOVA set of tools. So if you're not certain about this, just Google it and then follow the instructions for enabling that inside Excel. In this slide, we're going to give you an example then of how we can use an ANOVA for doing it. It's going to be a single factor one. We're going to use an example here where we have 3 different sets of data. So let's say they're prototypes. We've got 3 different groups of users to do it. They've rated their evaluation out of 5. And whenever we run the ANOVA inside Excel, it'll ask us for where the data is. Are we storing it in columns or rows? We can specify labels in the first column if we want to. The alpha value, then that's quite important because this contains, our error rate. So 0.05 here corresponds to a 95% level of confidence. And we then also specify where we want the results. Now, when you do it, you get quite a good chunk of information that comes out, and it actually can be quite useful if you have some data just to group it together, throw it into ANOVA and look at the findings that you see coming out. It can be a useful way of summarizing and exploring that data. In terms of what we have, so you can see through this here, we've got the different prototypes, we've got a count, we've got a sum, we've got average values, we've got standard deviations, so all useful stuff. And then down here we have a number of different measurements as sources of variation between groups, within groups, and other activities. You can have an explore about what all of those different aspects mean if you wish to. The only one I want to sort of highlight is the p-value, and I've bolded the value here because that's the one that we want to initially focus on if we're interested in understanding if there is significant difference between it. So if the p-value, if it's less than the alpha value, so this is our 0.05, then we can conclude that the means between the distributions are not equal. They are significantly different. So if our p-value is less than that critical error, we can say at that point, hold on, we know those means are different. Yes, we may then need to use a t-test to understand how they're different, but we know they're different. In our case, our p-value is 0.34. So that's actually quite a lot larger than 0.05. So we absolutely cannot conclude with 95% level of confidence that these means are different. And that's quite important because I suppose, you could look at them and you could say, well, the average 2.7, 3.4, 3.6, there does seem to be sort of meaningful differences between them. But when you do the analysis, you cannot be statistically confident at a 95% level of confidence that that is indeed the case. In fact, the p-value that's shown there is that you probably can't be much confident at all about the data in terms of it being truly different. So that's all we want to look at inside this section. It's quite a long one, quite a challenging one in some respects, but hopefully it really just is a matter of understanding, are we dealing with independent or paired samples? If we're dealing with 2 ones, then we use an appropriate t-test, just plug it in and then that gives us a result. If we have more than 2, we use the ANOVA tool, we get the results. Potentially then we do a few t-tests as well to tease things out. And in most cases, we'll just run those things, we'll do them quite regularly, and it will give us useful information then to understand when the values that we're calculating, the means, where they meaningfully differ between our different tests. So that's all we want to have a look at inside this section. In the next section, we'll go on to consider some of the other types of relationship that we can measure and model between values.